Hey guys, welcome to Digital Srini channel on YouTube, and please go ahead and hit the subscribe button if you haven't already done so, and do not forget to like these videos if you really happen to like them. Okay, in the last video I went through the paper, the original paper for cycleGANs, which is basically unpaired image to image translation, and in this video let's go through the code written in keras, of course in Python. Now I'm not sure if you have watched the previous video. I definitely encourage you to do that so you get a good understanding of what's going on when we are going through the code. But I'll quickly highlight a couple of things that I covered in the last video for those of you who haven't watched that. I definitely recommend for you to go back and watch it. This is not a reason for you to skip that video. So first of all, we are looking at translating images from one domain to another domain where we do not have any paired images for training. So that's step number one. And then let me skip through this. We are going to look at a few different types of loss functions. One is to ensure that there is cycle consistency. What does that mean? Well, when you convert, as the paper says, when you translate something from English to French and then back to English, then that English should match whatever the original English is, right? So that is one. And the other is we are going to use, instead of batch normalization, we are going to use instance normalization. And for discriminator, this is a 70 by 70 patch GAN, very similar to the one that we already discussed as part of our pix to pix. And another one, to reduce this oscillation, the discriminator is updated, not just on the generated image. Typically, how do you update a discriminator? You generate an image, which is a fake image, and supply that to discriminator. And then you generate you pick a real image, supply that to discriminator. And then the discriminator is trained on these real and fake images, so it can kind of get trained in identifying them. Now, here, they are suggesting that they keep an image buffer that stores 50 previously created images, and they use that to train the discriminator using the Adam solver and a batch size of 1. Okay, so couple other, this is very important, identity mapping. So when you provide a discriminator that is designed to generate Monet images, that discriminator expects a photo as an input, so it can convert that photo into something that looks like a Monet photo, Monet image. But what if you provide that discriminator a Monet painting as an input instead of a photo? It should do nothing to that input. It should provide the same input as an output. This is what identity mapping is. So this is another term that's part of our cycleGANs. So putting all of these together, again, there is this network architecture. Excuse me, we'll look at this in a minute. But putting everything together, we have a 70 by 70 patch GAN, and again, exactly same as pix to pix. As you can see the structure here, the only thing that's different is our batch normalization. Instead of using batch normalization, we are using instance normalization. And when it comes to generator is a bit complex. You have generator A and generator B. Obviously, one to generate images of one domain, the other one to generate images from different domains. So in our example, Monet paintings and photos. And the input to this generator comes from the other domain, right? So to generate Monet painting, you need to provide photo as an input, and so on, and vice versa for the other one. And for each of these generators, we have the corresponding discriminators that we need to train. And discriminator A is trained to discriminate between Monet pictures that are real and fake, discriminator B for the photos that are real and fake. And cycle consistency, we just talked about it. If you provide generator A with an input of photo, it generates a Monet painting. And when you put that Monet painting as an input to generator B generates a photo, right? So generator B always generates photos. That's what it's trained to do. Generator A always generates Monet painting. That's what it's trained to do. So when you stack them together like this, then your output photo must be consistent with the input photos. This is one of the losses that we minimize, and exactly the same thing for Monet painting. So this is forward loss, that's backward loss. And you have identity mapping, we already talked about it. So when you look at the generator architecture, they also mentioned that there are resonant blocks inside your architecture, and we are going to look at the 9 residual block architecture, where you have this residual block repeating 9 times right there. Otherwise, the structure has whatever they describe described here, 7 by 7 convolution with a stride of 1. That's your first layer. And then the subsequent layers are basically 128, 256, and then you have resonant blocks and so on. And how are we going to train the generator? Using 4 losses. One is adversarial, one is identity, and the other one is cycle loss, which is in the forward direction, and the cycle loss in the backward direction. So these are the 4 losses we're going to use, and this is how the composite model, or the combined model, if you want to call that, is going to look like. So while we are training generator, that's that we are trying to generate, for example, Monet images, Monet paintings, then all the other models should be kept constant or non-trainable. So that's what we are doing. So the Monet painting, for example, our generator A is trainable, and the generator B and the discriminator are non-trainable. Okay. For generator that generates photos, that's exactly the same. Then this would be the one that generates the photos. Then this is trainable, and the other 2 are non-trainable. And here is 4 losses that we define. So you have an input. For this generator, there is an output. Input for identity loss, output for identity loss, and so on. We put this model together to track these 4 outputs. Using these 4 outputs, we are trying to, and inputs, we are trying to minimize the difference between them. And how do we do that? Well, for the adversarial loss, we are going to use the L2 loss, which is basically MSE, means squared error. And all the others are L1 losses, mean absolute error, with a weighting of all of these as 1 to 5 to 10 to 10. So these 2 have equal weight, meaning cycle loss forward and backward equal weights, identity loss half the weight, and adversarial loss 1/10 of the weight compared to your cycle losses. Okay, so this is where we left off in the last video. Now let's jump into the code to get to the next level. Okay, so here is my code. Again, I use Spider IDE, but it doesn't matter. And if you wonder what version of TensorFlow, STF, I should have done this prior to the recording this video, but let's go ahead and look at this. This may be important 1-2 years from now when you are probably on TensorFlow 3 point something, but for now I'm using TensorFlow 2.4.1 and keras I think 2.4.3, but let's go ahead and confirm that. Import keras and keras version. Let's see, this is 2.4.3. Okay, so that clears that. Now let's jump in. So I separated this into a Python file that only has the model, and then I'm going to handle the data and then import the modules from this in a different file. I'm going to share all of these with you, so just watch this video for now. Okay, none of these should be surprising to you. This is in fact, let's just go through the code first and then execute them later. So we are going to import this anyhow in our other through our other files, so let's not execute them line by line, but let's understand them line by line. So we have let's say all this pretty much the standard, from keras.models. I'm importing model, input, con2d transpose, and leaky ReLU, because this is the activation we're going to use, and concatenate layers. I'm not sure if I end up using all of these, but we'll see that in a minute. One important thing that I'd like to mention is instead of batch normalization, we will be using instance normalization as recommended in the paper. Where do you get instance normalization? This is not part of your keras.layers, so there are a couple of things that you can actually do. You can go to you can install keras_contrib using these guidelines that are provided at this link, or you can download the code from the link above. So what I have done is download instance normalization code from here. Let's go here and let's open. So I opened these two. First of all, keras_contrib right there. So if you just go here, there are instructions in terms of how to install this keras_contrib, and then in here you have your instance normalization. Instead of doing all of that, I just went to like right here, and I just copied this entire code. Okay, so this is instance normalization.py. So I just saved that as part of my directory. So you should see instance normalization.py right there. So when I go to my code, I am just importing instance normalization. So it should work right away. Yeah, so that's the only tricky part. Everything else should be straightforward as we have discussed. So let's go through our discriminator first. Again, this is our patch GAN 70 by 70 patch GAN. And if you don't know what I'm talking about, then go back 2-3 videos where I talked about pix-to-pix and I introduced the concept of patch GAN in that video. Okay, so here it is. And again, what is a discriminator? It's just a binary classifier where it's trying to classify it between real or fake. The only difference here when it compared to pix-to-pix is we are using instance normalization that we just imported. Okay, and also we are using leaky ReLU, which is same as the one that we have used in our pix-to-pix with a slope of 0.2. Anything else worth mentioning? I don't think so. Everything else makes hopefully makes sense for you for each model. That's it. And then we are defining our ResNet block because we need the ResNet block as part of our generator. We just talked about it. And what is a ResNet block? A residual network, which is basically you have a couple of convolution layers and you take the output and you concatenate the output with your input. So that's exactly what a ResNet block is. That's exactly what we are doing here. And we are going to call this as part of our generator, which is down here. And we are just following whatever the paper described, which is, I think this is exactly what we are trying to follow. C7S1, 64, that's what this is, 7 by 7, 64, and then comes, D128, D256, R256, and then a few ResNet blocks. How many? 9 of these, because we are following this 9 residual block. That's it. And everything should be, we just discussed this, so I'm going through this a bit fast. And now also looking at the composite model, we also looked at this. The key point here is making this model trainable, the one that we want to train in this as part of this composite or compound model. And then the corresponding discriminator and the other generator are kept non-trainable. That's it. And we have our adversarial loss, inputs and output. We have our identity loss represented by the input and output here. And you have your cycle loss forward, cycle loss backward. So you have 4 outputs. All those 4 outputs are shown here. So output D, which is our available for our GAN training, GAN loss. This is, we are using mean squared error to minimize that. And for all the other ones, we're using mean absolute error. Or if you prefer the terms L2 loss and L1 loss, you can do that. Yeah, this is your L2 and this is your L1 loss. And they're weighted like this. And again, we recently discussed this, so let's move on. What else do I have here? A few helper functions. First of all, our output right here, if I can go back, is our generator is the final activation to our generator is tan H. And tan H goes from -1 to 1. As you probably know. Sigmoid, if you're using that, goes from 0 to 1. So if you're actually scaling your images, using sigmoid, then you should divide all your pixel values by 255, assuming your input is 8-bit. So your values are scaled to between 0 to 1. We want our values to be scaled between -1 to 1 in this specific case. So that's exactly what we are doing here. Instead of dividing each pixel by 255, we're subtracting 127 and dividing by 127.5, right? So that's basically scaling it between -1 to 1. So that's what happens when you load the real samples. By the way, we are loading 2, right? We are loading x1 and x2, and each of these we are kind of scaling, and this returns your both inputs right there. And then we have a couple of helper functions, one to generate real samples. Again, this is very similar to any other GAN that we have done. Our discriminator needs 2 inputs, one real input, one fake input. So that's what we are trying to generate here. A real input is basically sampling from our original data. A fake input is using our generator to just go ahead and predict on the real data, so you get a fake input that goes into your discriminator. So you generate real samples and generate fake samples. Now, I think I'll get to that in a second. But by the way, we are not feeding these fake samples directly to the discriminator. If you look at the paper that we discussed, they have a buffer of 50 images. I guess we'll get to that in a second. But this one gives us fake samples for now. Think of that. Okay, just fake samples. And also the real samples. When you train a discriminator, you need to tell the discriminator that this is real sample. How do you do that? Well, by setting the label to 1. This is how you tell the discriminator that these are real. And by setting the values to 0, you're saying, hey, these are fake samples. So this is how you're training the discriminator. Okay. Now moving on to the next helper function. Again, this is very straightforward. Save the model. When I call this function, go ahead and save these models 1 and B and 2. Right? We have two generators, one that takes us from A to B and the other that takes us from B to A. Go ahead and save them with a file name of generator model A to B and insert whatever the iteration number is right there. Yeah, so it saves them with an iteration number. So when you save these every 100 epochs or iterations, at least you know that, okay, these are the models at that specific iteration. So that's what this helper function is doing. And then we have another function that summarizes the performance. What do we mean by that? Well, basically go ahead and save two plots. One, a plot of some random images that get converted from A to B, and same thing B to A. So it's going to save these plots however often we call them. So this is another helper function, and we are giving unique names, so we are not overriding the same thing over and over. That's all this part is. So now next comes the supplying 50 images. Right, so how do we supply these pool of 50 images to our discriminator? So this is our image pool or image buffer, if you would like to call this. So this is the 50 previously created images, and then we are basically creating an empty list, and we are populating that with your images right there. Okay, so that's the helper function, where we again maintain a list of 50 images that we are ready to provide as input to our discriminator. 50 fake images, I should say. Okay, now comes the training part. Again, this is very similar to our training in pix-to-pix or conditional GAN, where you have you define your number of epochs, and by the way, the number of batch size equals to 1. Again, I discussed about this in pix-to-pix. Even there we use a batch size of 1, and apparently that's great batch size if you're actually trying to generate a decently high resolution type of images. So let's stick with batch size of 1. And what else? Determine the output square shape of the discriminator, and we are providing our data. Our data set is basically a list of training A and training B images. Yeah, that's our data set. So we are unpacking that right here. And then also we are starting with an empty list for pool A and pool B. These are the 50 fake images that we are holding to provide as an input to our discriminator. Yeah, so that's what that is, and this is straightforward, batches per epoch. And by the way, our batch per epoch should be equal to our training size. If you have 1000 images, then you have 1000 batches per epoch, basically, or iterations per epoch, if you want to think about it, because our number of the batch size equals to 1 here. Yeah, so just a quick note there, and number of steps. And finally, for each iteration, not each epoch, and for each iteration, right, that's the number of steps we have there, do the following. What are we trying to do here? First, you need to train the discriminator. Again, you train the discriminator by providing real images and fake images. So first, we need to generate real images. This is exactly why we have our helper function called generate real samples. You saw that up there. So using that, we are going to generate A, X real A, and Y real A. Yeah. And again, what is Y real A? When it says real, it's 1, right? We are saying that this is a true image. So our X real A is an image coming from our train A. So think of these as Monet images, real Monet images with a label of 1, and these are real photos with a label of 1, because this is still real. And then we have fake Monet images with a label of 0, fake fake photos with a label of 0 right here. How do you get fake photos? You generate fake samples right there. Yeah, so generate fake samples, and again, if you forgot that function, generate fake samples is basically using your generator to predict on a given data set that you provided. That's it. Yeah, so this is the output of your generator. That's what you're looking here. Okay, so this is your fake. Now again, you're not providing these fake images directly to the discriminator. In fact, you are providing a pool of images. So you take this X fake A as the input, and then pool A, and you basically update the image pool. Exactly the same for your B images. So both for your Monet images and both for your photos, you do the same. And now you are training your model, your combined model right here, from B to A, and it's training on these, and you're training your discriminator model A and training on your batch right there, on the real data. Sorry, I should have mentioned that. And then you're training the same model on the fake data, right? And remember, you're providing X fake A right there, and then Y fake A, which is basically a value of 0. And X fake A is image pool. I hope so far so good. And then you're looking at your generator loss 1, and this is your generator loss 2. There you go. And pretty much the same process as your, instead of B to A, now you're training A to B. Okay, and discriminator loss DB, or discriminator for the B loss 1 and discriminator for the B loss 2 on real and fake. Again, every time you have a discriminator, you're training it on real, and then you're training it on fakes. So you have your for B to A model, and there you go, discriminator for A, because you're generating A images when you go from B to A, right? So you're generating A. That means you have to train the discriminator A. Here you're generating B images, so you have to train model B. Please go through this code again carefully if these things are not clear, and then hopefully it gets clarified. Anyway, so you're training your discriminator, so your generator and your discriminator, and basically at the end of this we are printing our what is this iteration. So if you have 1,000 images, you have to or I think I mentioned that here. If you have 100 images with a batch size of 1, in one epoch you have 100 iterations. So every 100 iterations, it's one epoch. So if you say, oh, I want to do my training for 50 epochs, then you'll have 5,000 iterations that you have to keep track of on the screen. Just again, a quick note. And after every batch per epoch, we are actually summarizing the performance, meaning after every 100 images, if I have total 100 images in my training data, of course I have probably 5,000 images, but whatever that, at the end of it, go ahead and summarize the performance, which is nothing but save your, use your generators to generate these images and then save those as PNGs. That's what that summarizes. And every time, for example, again, if my if I have total images as 100, after 500 iterations, go ahead and save the models. You don't want to save models after every epoch. You want to save the models after every 5 epochs or 10 epochs. That's exactly what we are trying to do here. So this is the cycleGAN model. Now let's go to Monet to photo. This is the interesting, fun part. So now that we have our model, now let's go ahead and get our images ready. So first of all, where do you get your data set? So I am going to leave this link as part of the description. So when I click on this, in fact, I may have already opened it right there. You can see they have a whole bunch of photos. You can convert apples to oranges. You can do cityscapes. You have iPhone to DSLR flower. I don't know what that is. Horse to zebra is something I tried, and that's a fun one. And we are going to use Monet to photo right there. Yeah, and you can also do summer to winter and so on. It's up to you. So what I've done is I downloaded this Monet to photo, and let's look at the folder right there. And I extracted the zip folder, which means I have this is what I saw. All of these will be extracted. So there is test A with how many ever 121 images, and train A with 1072 images. Yeah, so there is train A and test A, and there is train B. These are regular images, regular photos, not Monet paintings. There are 6,000 of them. So the data set is not balanced. Obviously, there are not. We don't have infinite Monet paintings. We have infinite pictures. We don't have infinite Monet paintings. We only have finite. In this case, we have about 1072 plus how many ever we have here. So the data set is a bit unbalanced, but we can subsample. We can basically say, okay, I just want 1600 images from here, 1600 from the other one. Now you have a good understanding of the data set. Let's get back to the code and let's start running some of these lines there. All I'm trying to do is now just for example, image to array and load the image. And that's exactly what I'm trying to do down here. So my path is Monet to photo. That's the directory where I have these images. And I'm going to load all images. Yeah. And then I am going to subsample 500 of them. Why did I do that? So I can just do the training in a decent amount of time. You use all the images that you have. That's my recommendation. I only used 500 images, and in fact I already loaded the data, so it's faster for me to demonstrate. So my data A, if I can find it, data A is 500 images, each image 256 by 256 by 3. But I have 1072 images for Monet paintings. Same thing with my data B. For actual photos, there are 6,287. I am only using 500 of them. That, in a way, my data is balanced, but I don't have a lot of images. So the training is not that great. It can be better, but this is enough to demonstrate. So from that point, once we load the data, let's go ahead and have a quick look at a few of them. So there you go. So these are some of the images. Let's go ahead and load one more time so you can see. So on the top you have Monet paintings, on the bottom you have photos that also look very close to Monet painting, but they're actual photos. Okay. Now let's create remember our data set. I'm just providing that as a list of A and B. So let's create a list of A and B right there, data A and data B. And just to give you the shape of these, so we have 500 images, each 256 by 256 by 3. Two of them, one for Monet paintings, one for our images. Okay, the next step, we have to pre-process these images right there. So that's the function, helper function. In fact, I could have actually called that from our other file, but that's okay. Let's go ahead and pre-process the data. So all of our data will be converted from unsigned integer 8s to floating point numbers that go between -1 to 1. So we are almost ready. So from my cycleGAN model, which I just described here, right from here, let's go ahead and import my defining the generator, discriminator, composite model, and all the other functions that we need. And then let's provide the right inputs. What is my image shape? My image shape is 256 by 256 by 3. Why do I need that? Because that's what goes into your define generator, right? So when you go back and look at define generator, some of you may think I'm too slow, but it helps sometimes. So define generator, you have to provide the input shape so it can create its model. That's exactly what we are trying to do. Input shape is 256 by 256 by 3. So you can just define your generator, and then you define your generator for B to A, which is exactly the same. And then you define your discriminator by giving the image shape, and same with discriminator B for image shape. And now we have to define the composite model. So for the composite model, let's go back. Here's the composite model. You have the generator of interest, the first generator that we are trying to train, and the corresponding discriminator model, and the other generator and the image shape. The discriminator and the other generator are non-trainable, and this generator is trainable. So we are going to call this function a couple of times. So let's come back here. Define composite model for A to B. For A to B, our generator model A to B is of interest, so that goes first. The discriminator model B, because we are going from A to B, so the discriminator is B. And then this other model that we don't want to train, but we still need it to generate some images, is the B to A. This is not trainable. And finally, the image shape. This is my combined model A to B. Now you define your combined model B to A. For this one, the first one is B to A. we're calling the same function, but this time the model of interest is our generator that takes us from B to A, and then the corresponding discriminator is the one that discriminates A, and then the other model is A to B, and so on. So let's go ahead and call this, define this model right there. Once you have that, now let's just call our train function right there. Train, we took so much time trying to define and understand this train. What does it take as input? Your discriminator for A, discriminator model for B, generator A to B, generator B to A, combined model A to B, combined model B to A. All of those we are providing right here because we just defined them up here, and now you can go ahead and train it. I'll stop this in a second, but let's see how the training goes. Let's go ahead and run these lines. I have already trained this for 50 epochs. So let's look at the results. Again, the more training, the better it is, because you're trying to find a balance between generator and discriminator, right? So the more training, the more balance it's going to achieve. Okay, so it just started there. As you can see, iteration 1, 2, 3, and the losses for discriminators and the generators are printed after every iteration. These are not epochs. So this is not going to stop after, what did we define for our number of epochs? This is not going to stop after 5. Obviously, it's continuing after 5. So how many iterations do we have? We have 500 images. So 500 iterations, and it's going to do that 5 times. Yeah, so we are going to see 2,500 of these. Obviously, it's going to be very slow. So let me go ahead and stop this because I have already done that before. So now let's import whatever we saved. So at the end of this, it saves your generator models for A to B and B to A. And we are not even saving discriminator because that we don't need them. So let's import our generators and start generating some Monet images or photos from Monet images. So first of all, let us import the required libraries. And this function is just to select a random image out of the collection of images we have. And this function is to plot the output. Yeah. And here is where we are defining the data. So of all the data, let's just get, remember from all these images, we selected 500 images for training. Now I'm just selecting 50 images just for testing, yeah, from our big data set. So this is one way of doing things. And once you select those, you have to scale them exactly the way you scaled the images for training, which is between -1 to 1. There you go. And now let's go ahead and import our model. In fact, you can actually say here that you don't want to load the, you just want to train your model. Sorry, you don't want to train your model any further or something. But anyway, if you do not provide your instance normalization here, then it's going to throw an error saying, hey, I don't know what instance normalization is. So we are providing this exactly what that is. That's that line, and we are loading both models, A to B and B to A. Yeah. So once you load that, now I just need to predict. That's it. So first of all, let's get a real image for A, and then use that as input for A to B and convert our A into B. That's what this is. And then also we can reconstruct it, right? So just to check this cycle consistency, which is now let's take B generated as an input for our model B to A, and then print out reconstructed. And then we are going to plot all of those. And let's do exactly the same, starting with B instead of starting with A. That's what these two are. So first, let's only look at one. So it makes a bit more sense for us. So let's go to plots. So there you go. So this is our real image. This is how it would look like if it were a Monet painting. And this is the original image reconstructed. Obviously, the cycle consistency is not good because my reconstructed is not pretty close to what my real is. So I should have trained this for another 50. These things take a long time for training. I just stopped it after 50 epochs. And GANs are extremely slow. They're painfully slow. So another image right there showing you, or actually a couple of images right there, showing you the real also looks like painting, and how Monet would have painted that, and when you reconstruct it back right there. So let's look at starting with B, from photo to Monet. From real to generated to reconstructed right there. So let's go back and look at some of these. real photo, and there's Monet, and there is reconstructed. So yeah, that's not bad. Real to Monet to reconstructed. Okay, so you can play with this, and I was also playing with a just a custom image. I just Google searched for sunset, and I downloaded an image. In fact, you probably saw that as part of my folder right there. I just downloaded this so I can test how it looks like if it's a Monet painting. And I also took a picture of what you see behind me right there, and that's the picture. And let's see how this looks like, the sunset picture. There you go. Yeah, so that's the original picture, and this is how Monet painting would have looked like, and that's the reconstructed. Reconstructed is not that bad, that different from the real one. Yeah, and you can also test with your own images. Again, what have I done here? I just loaded the image, scaled it to -1 and 1, and everything else is pretty much the same. Now, if you're curious about Srini to Zombie, I have this was pretty painful, but I was too interested in it, so I went into I Google searched for a whole bunch of zombie images, and I only got like 40 or something right there. And when I saw the, you know, literally I took my snipping tool and got you know, a small face area, saved it, and I wrote a piece of code that kind of resizes all these images to 256 by 256. And I did the same. In fact, I should have done with this with human faces. I just have my own faces pictures, so I just trained it with this. There's only 20 of my face images, and zombie I only have 50 images. One of those is my face, in case you're curious. Zombified. But anyway, I took these and as inputs, and we may as well test it out. While I'm not sure how many of you are still sticking around, but if you are curious, let us go ahead and do all the way up to this point. Go down here. I don't have many images, as you can see, and let me run these lines again. The code is identical, so I'm not even going to go through the code. Obviously the models are different, so again I think I did only 50 epochs, so let us run these lines so you can see. Let's see, it's loading. I mean, these are, so there you go. That's my input image. This is what I think it's I would look like a zombie, and this is the input image reconstructed. So the cycle consistency seems to be pretty good. If I go from here to there, this is not bad. But let's load another image. Oh, I'm loading the models again. I shouldn't have done that. So this is my face, and there's you go, me as a zombie. It's not great. Again, I don't have many images, but it actually got ugly hair and some stuff going on here. So anyway, this is something I was curious about, and it's doing a decent job. So be creative, try to find other examples and see how this can be very useful for you. Apologize for this very long video, but I hope you found this to be very useful if you're interested in this cycleGAN type of GANs. So in the next video, let's cover a different type of GAN again. Let's stick with this topic for at least one more, if not a couple more. So please go ahead and subscribe to this channel, and let's meet again in the next video.